the 200-degree impossible atmosphere. TOI-561b is a rocky super-Earth that should be a bare, charred husk. Yet new data reveals it is wrapped in a thick, persistent atmosphere. Orbiting its star once every 10 hours, this world sits 40 times closer to its sun than Mercury does to ours, facing a relentless solar wind that should have stripped its gases away billions of years ago. Last week, researchers analyzing the latest JWST-NIR spec data confirmed that this 200-degree Fahrenheit lava world is significantly cooler than a bare rock should be. This temperature gap is the first proof that a thermal blanket is actively fighting the star's heat. Understanding this survival starts with the missing one, 700 degrees. The missing one, 700 degrees. If TOI-561b were a simple airless rock, physics dictates its dayside would hit nearly 900 degrees Fahrenheit, a temperature high enough to vaporize titanium. However, the May 2026 data release from the James Webb Space Telescope shows a much lower reading of 200 degrees. This discrepancy isn't a measurement error, it is the fingerprint of massive heat redistribution. A thick, volatile-rich atmosphere is acting like a planetary air conditioner, catching the incoming solar radiation and pumping it toward the freezing night side through high-speed winds. Think of it like a convection current in a blast furnace. Instead of the heat localized on the face pointing at the star, the gas layer smooths out the thermal peaks. This suggests the atmosphere isn't just a byproduct of the planet's heat. It is an active engine that keeps the surface from reaching its theoretical melting limit. But this raises a second problem. Even if the gas moves the heat, it should still eventually leak into space, which brings us to the mechanism of the magma-atmosphere equilibrium. The recycled sky. The atmosphere survives because the planet is a wet lava ball that constantly replaces what it loses. As stellar radiation strips gases from the top of the sky, the global magma ocean below outgasses new material to fill the void. It is a continuous loop of evaporation and absorption where the liquid rock serves as a deep reservoir for volatiles like water vapor and carbon dioxide. This chemical exchange means the atmosphere isn't an ancient leftover, but a freshly manufactured layer in constant flux with the interior. The galactic thick disk anomaly. The chemistry of this world is fundamentally different from anything in our solar system because of its age. TOI-561 is a galactic thick disk star, meaning it formed 10 billion years ago when the Milky Way was young and lacked the heavy metals common today. Because the star is iron-poor, the planet is surprisingly low density for its size, which actually helps it hold onto its gas. A lower iron content in the core changed the internal pressure of the mantle, allowing more volatile gases to stay trapped in the rock for eons. This ancient survivor has had twice as long as Earth to lose its atmosphere, yet it remains one of the most volatile, rich, rocky worlds ever found. This persistence suggests that our models for how planets die near their stars are missing a major variable. The survival of TOI-561b changes our entire strategy for finding habitable worlds. The part no one wants to say. The discovery of a stable atmosphere on a 200-degree world proves that the cosmic definition of a dead zone is a human construct. By looking at the heat redistribution seen in the JWST data and the magma-atmosphere equilibrium that sustains it, we have to accept that rocky planets are far more resilient than our previous models allowed. If a world blasted by 40 times the radiation of Mercury can maintain a thick gas envelope for 10 billion years, then the habitable zone is likely much wider and more complex than a simple distance from a star. This forces a strategic pivot for future missions. We can no longer ignore ultra-short-period planets as mere burnt cinders. They are potentially active laboratories for secondary atmosphere formation. This means the hunt for life shouldn't just target Earth-like temperatures, but also these high-energy equilibrium states, where geological activity and atmospheric shielding create a unique, stable niche. Watch for the Cycle 5 spectroscopic results this summer, as they will likely confirm if this wet lava ball has the specific heavy molecular signatures needed to rewrite our planetary formation textbooks forever. Subscribe for more.